Hey everyone, it's Professor Davis again. This time I'm going to talk to you a little bit about elimination reactions. But before I do this, I would recommend anyone who has not yet watched the SN1, SN2 video at my channel, Chem Survival, check that out now, because I'll be referring back to that lecture a little bit as we go. So let's start our elimination reaction discussion the same way we did our substitution reaction discussions. Talk about a cast of characters. The first of which is the base. There will be a Lewis base in every elimination reaction, which can easily abstract a proton from substrate by donating electron pairs to form a bond to that proton. So we're looking for species with high electron density, available lone pairs which can make a new bond to a proton. Sounds an awful lot like a nucleophile, doesn't it? Next I'm going to define something called the alpha proton. An alpha proton is a proton which is bonded to the carbon adjacent to the electrophilic carbon on the substrate. So anytime we refer to the alpha position to any functional group, we're talking about the position which is one carbon bond away. And finally, the leaving group, which just as in substitution is going to be a substituent which easily withdraws its bonding electrons to form a separate stable species. So now that we've defined the important characters and players in these elimination reactions, let's take a look at a few generic examples. The first mechanism we're going to discuss today is the E1 mechanism. An E1 mechanism has a tendency to occur when we have a weak nucleophile, a highly substituted electrophile, and a fairly good leaving group. So we have most of the ingredients necessary for an SN1 reaction, but we don't have a very good nucleophile. And let's take a look at how that affects this reaction. So let's say that I've got a T-butyl halide, as in this example, but instead of a stronger nucleophile, I've got something like phosphate anion. Now, phosphate anion has an abundance of lone pair electrons and a high negative charge, but those electrons are distributed around a very large volume within the phosphate. And furthermore, they're delocalized by resonance, which attenuates their nucleophilicity. So phosphate anion is very unlikely to act as a nucleophile. So let's change this back to a simple green sphere so we can watch the reaction occur. In the case of the E1 mechanism, just as in the SN1 mechanism, the reaction initiates with the departure of the leaving group. When this occurs, a carbocation is formed. Now, we have several options with what we can do with this carbocation. The first of which is, of course, we can have a nucleophilic attack. This would be an SN1 reaction. So if I have a relatively good nucleophile, I can expect a substitution product to form. But remember what we said about phosphate anions in similar species. Their electron density is distributed so widely around the species that there really isn't a good nucleophilic site. So instead, it's going to react as a base. The base will abstract an alpha proton from our carbocation, and in doing so, it will initiate the formation of a pi bond between the alpha carbon and the carbocation center. Now let's watch that happen now. So you can see the consequence of this reaction. We've created an alkene, or a hydrocarbon containing a double bond. And we've done so by proceeding through a carbocation intermediate. So now let's take a look at the E2 mechanism using a similar substrate so that we can see the difference. In the case of the E2 mechanism, we're usually dealing with a bulky base, or a bulky nucleophile, one which contains lots of entangling appendages which make it difficult for the lone pair electrons from the nucleophile to access the electrophile. So here I've used what looks like another T-butyl halide. In this case, I've placed a poor leaving group on, and I'm going to use a really large, really bulky nucleophile. A great example of this is diisopropyl ethylamine. You'll notice that the electron pair, which is on the central nitrogen, is buried deep within the molecule. And this means that it's going to have a great deal of difficulty accessing the electrophilic site on our substrate because of all those large steric blockages that are going to occur as it approaches. So all these sterically hindering groups mean that diisopropylethylamine can't really react well as a nucleophile. So instead of having a situation where my nucleophile attacks substrate, I've created a situation where this is impossible. And instead, my nucleophile will act as a base, abstracting an alpha proton, which is out near the perimeter of the molecule and therefore much more accessible to this bulky base. So in this case, we're going to find the alpha proton, which is at a 180-degree dihedral from our leaving group. This is because removal of the alpha proton is going to initiate departure of the leaving group in a cascade of electron flow. And the mechanism for it looks something like this. Our diisopropylethylamine or similar bulky base will abstract the alpha proton, simultaneously creating a double bond and ejecting the leaving group in a single concerted step. Let's watch that happen now. You'll notice that the product that we formed in this case is exactly the same as the product which we formed in the E1 mechanism. This is because of how simple our substrate is. One could imagine quite easily how going through a carbocation intermediate versus having this mechanism occur in a single concerted step through removal of an alpha proton in the anti-conformation could create potentially different stereoisomers. Not to mention that since the E1 goes through a carbocation, there are potential rearrangement products. So even though I've created the same product in this case, it's important to note the differences in the mechanisms because they will lead to different products in certain situations. So now that we've had a look at each of these two reaction mechanisms in action, let's think about the factors which affect them. First is the mechanism. The E1 reaction occurs as a two-step mechanism going through a carbocation intermediate. This means that the E2, of course, happens in a single concerted step, much like our substitution reactions did. Because of this, we expect similar kinetics rules to apply. That is, first-order kinetics for the E1 and second-order kinetics for the E2. In the case of potential stereochemistry, since we're creating alkenes during elimination reactions, we have to ask ourselves if there's a potential for EZ isomerism. With the E1 reaction mechanism, there is no stereospecificity. However, in the E2 reaction, we can get stereospecific reactions if we start with a chiral starting material. Carbocation rearrangements are common in E1 reactions because they proceed through carbocation. However, because the E2 happens in a concerted step, there is no opportunity for rearrangement to occur. As far as conditions which promote each of these reactions, we expect to have a very weak nucleophile for E1 and a relatively weak electrophile or nucleophile, for E2. That same species, which is a very weak nucleophile, should act as a relatively decent base. But remember, in an E1 reaction, if our base is really strong, we're going to start pushing ourselves in the direction of an E2 reaction. An example of this would be using phosphate ion to promote E1 or diisopropylethylamine to promote E2. From the perspective of the substrate, we expect an E1 reaction to have highly substituted electrophiles and unobstructed alpha protons. This leads to easy formation of carbocations and easy deprotonation of the alpha proton. In the case of E2, electrophiles can be less substituted because no carbocation needs to form, but we still need that unobstructed alpha proton, which can be accessed by the bulky base. And finally, the leaving groups. In the case of E1, we want a good leaving group to promote carbocation formation, while in the case of E2, a poor leaving group is better because that will hang on until the alpha proton is abstracted. So this gives you a rough idea of how the E1 and E2 mechanisms occur and what sort of conditions and reagents we can use to promote one or the other to take place. And that's all for now. We'll see you next time.